Today, we're taking everything you've learned about renewable energy engineering and pulling it all together. We're turning those complex theories into a fully bankable, real-world utility project. We're going to walk through the exact same workflow used by professional EPC companies, engineering, procurement, and construction, taking a 60-megawatt peak project from its very first design assumption all the way to that final investment decision.
To truly grasp the massive stakes of this workflow, we really have to start with the bottom line. We are looking at a staggering $63.34 million total capital expenditure. When you're engineering at this scale, every single calculation, every software simulation, and literally every equipment choice you make directly impacts millions of dollars.
But hey, the payoff for getting that engineering right, it's absolutely brilliant. This optimized plant is going to deliver a combined annual energy production of 93.9 gigawatt hours from our integrated system. I mean, that is just a phenomenal amount of clean, reliable energy. So how do we get there? We're going to reverse engineer these numbers following this 5-step roadmap: utility-scale PV plant design, BSS sizing and integration, engineering deliverables and BOM, project CapEx and OpEx, and finally the big one, the final financial evaluation.
Let's kick things off with Part 1, Utility-Scale PV Plant Design.
Now, professional design doesn't just start with how much land you have, it actually starts with the grid impact study, which dictates our maximum export capacity. Based on those network limits, we size the plant at a truly massive scale. We're talking nearly 97,000 PV modules, 620-watt peak each, feeding into 1,680 string inverters and 6 9-megavolt ampere transformer stations. All of this comes together into a beautifully coordinated 33 kilovolt medium voltage collector system.
And check this out, our 1.19 DC to AC ratio, that is definitely not a random number. It's engineered specifically for Egypt's unique medio-norm irradiance profile. It hits that sweet spot, ensuring we don't clip too much power at peak hours while maximizing the inverter use all day long.
Moving right along to Part 2, Utility-Scale BESS Design.
Here's the thing about modern utility plants. The battery isn't just a simple energy bucket anymore. We design it as a dynamic grid support asset, sized for 20 megawatts of peak shaving, 38 MVAR of reactive power support, and absolutely crucial network voltage regulation. It's actively curing grid instability. Plus, a neat little bonus, during construction and operation, this same system can actually supply temporary site loads and EV charging infrastructure.
To pull that off, we are relying on some heavy-duty specs. We're using a 20 megawatt-hour lithium iron phosphate, or LFP battery, paired with a massive 45 MVA bidirectional power conversion system. By utilizing an AC-coupled topology with staged augmentation and full EMS, BMS, and SCADA integration, this setup smoothly delivers vital output exactly when the grid demands it.
All right, on to Part 3, Engineering Deliverables and BOM. This is where we bridge the gap between software analysis and actual procurement. It's a complete software-based workflow. We start off with SketchUp for our 3D layouts and shading analysis, and PVSys for energy yield simulation. Next, we use AutoCAD to draw up our single-line diagrams, or SLDs. From there, we generate a highly accurate material takeoff and bill of quantities, literally the exact list of parts we need. All of this culminates in a complete, construction-ready engineering package.
Which brings us to Part 4, Project CapEx and OpEx. With all our deliverables locked in, we can finally calculate the hard physical costs. As you can see, electrical equipment absolutely dominates the budget here. It eats up $49.4 million. That's nearly 78% of our massive $63.3 million CapEx. The civil and structural work? Just a fraction of that. This highlights perfectly why optimizing your PV and BESS sizing in those earlier software steps is so critical. I mean, this is where the vast majority of the investor's money is going, right?
And when we flip over to the operational side, the OpEx, some really fascinating real-world details start to emerge. The total for year 1 is $1.5 million. But look at these specifics. We actually have to budget $180,000 just for robotic module cleaning, running 12 times a year, simply because this plant operates in a harsh desert environment. You've also got significant all-risk insurance and dedicated BSS maintenance for things like cooling fluids and BMS calibration. Because, engineering isn't just about building the thing, it's about keeping it running efficiently for decades.
And finally, Part 5, the final financial evaluation. Now we reach the absolute climax of our whole workflow, proving the financial bankability of our engineering design. This dashboard is exactly what you'd put in front of the stakeholders. It beautifully brings together every single technical calculation, every PV-SYST simulation, and every financial metric into one complete view. We've got our energy output, our project CapEx, and our OpEx, all seamlessly flowing into those final profitability metrics.
Let's break down the cash flow. By comparing our total annual cost against our annual energy output, we hit an incredible levelized cost of energy, or LCOE, of just 6 cents per kilowatt hour. Now factor in a power purchase agreement selling price of 12 cents per kilowatt hour, and our revenue sits at $11.45 million annually. That absolutely dwarfs our operational costs of $1.5 million, meaning we're generating a really healthy, consistent net profit year after year.
And because of all those rigorous, optimized engineering choices we made back in phases 1 and 2, our investors are rewarded with a fantastic 15.7% return on investment. In the utility infrastructure world, that is a highly attractive figure. That's the kind of number that secures project funding.
It gets even better, because the system generates so much net profit that entire $63.3 million CapEx actually pays for itself in just 6.37 years. A payback period under 7 years on an asset designed to last 25 years, that is absolute music to a developer's ears for sure.
And over that 25-year lifespan, once that initial CapEx is completely paid off, this perfectly engineered plant goes on to deliver a staggering net present value of almost $86 million. If there was ever proof that high-quality engineering isn't just a technical requirement, that it's literally the fundamental driver of massive financial value, this is it.
So we've gone from a basic grid study to equipment sizing to software deliverables, right down to generating an $85 million NPV. Rather than just learning isolated calculations, you've now seen how to engineer a complete power station. So the real question is, how will you apply this comprehensive EPC methodology to engineer and evaluate your own future utility-scale projects?